Hello, this is the age and distance of an open cluster team. My name is Ludan Alsoudani, and my teammates are Mohammed, Maureen, Juan, Oren, and Yury. And then our team mentor is Miss Olivia Kuper.
We start off with an introduction to what open clusters are. Open clusters are loosely bound groups containing anywhere from tens to hundreds of stars. These structures are not stable and they will eventually disperse, meaning that open clusters are mostly found in spiral or irregular galaxies because these are the galaxies in which stars are still forming, as opposed to being found in elliptical galaxies, galaxies in which star formation no longer occurs. Open clusters are typically younger than globular clusters, and within our own Milky Way, there are around 150 known open clusters. As for how open clusters are formed, all the stars in a given open cluster are formed by the same molecular cloud or nebula. Gravity groups the dust together, and this cloud collapses once a minimum submass is reached, eventually forming a star as seen in B on the image to the right. Eventually, the amount of stars in an open cluster ranges anywhere from 10 to 10,000 stars. Stars eventually do disperse from the open cluster after a few 100 million years.
Composition of an open cluster. The majority of open clusters disperse prior to the majority of stars reaching the end of their life cycle, resulting in a prevalence of young stars with most clusters. Additionally, young open clusters are characterized by a higher abundance of blue stars, whereas older clusters predominantly host yellow stars. Lastly, open clusters are less densely populated in comparison to globular clusters. Where can they be found? Open clusters within the Milky Way are typically found in a dense region of the galactic disk, where layers of stars, gas, and dust partially obstruct our view. Due to their location, these clusters are susceptible to being gradually disrupted by the gravitational influence of passing objects, explaining why most open clusters are relatively young, with ages less than 1 billion years. In contrast, older star clusters are situated further away from the galactic.
GC1245 is an open cluster first discovered by William Herschel in 1786. It's located in the Perseus constellation and is estimated to be over 27 light years across. There are officially 506 stars in LGC1245, but we decided to exclude 15 of the cluster as they were too faint to perform photometry on. In order to efficiently analyze each star correctly, we used Shikharimi's numbering system from the paper La Masio Galactico. We sourced our data from the telescope located in the Roque de los Muchachos Observatory in the Canary Islands. This telescope belongs to CERA, an organization of universities including Florida Tech, Eastern Tennessee, and others. CERA allows smaller universities to have access to telescopes in order to further their astronomical departments while keeping costs manageable.
In order to properly analyze our data, we use photometry and filters. Photometry is a measurement of light as data to analyze and gain information. We used images taken by our telescope with filters that work by taking all but a certain range of wavelength, which changes with each filter. Images of the cluster were taken through the B or blue filter and the V or green filter, and they will be used to obtain the color index and spectral type of the star. We use a reference star to find the magnitude of the target star's and Astro Image J because its magnitude is known for each filter. Astro Image J being the application we use to analyze our data. In order to find the age of NGC, we have to begin by analyzing the B and V filter calibrated telescope images using the multi-aperture photometry feature in Astro Image J. Most stars were found on the 1/22nd exposure images, while dimmer stars were found using the 90-second exposure images. The apparent B and V magnitudes of every other star were found in comparison to our reference star 125, as the magnitude of that star was already known. The B minus V was calculated to find the color index of each star, which will then be used for the spectral types.
However, we can't use the raw B and V counts from Astro Image J because of reddening. So interstellar dust clouds absorb, scatter, and redden light. This is because red light has a longer wavelength than blue light and is more difficult to scatter. That's why when you look outside, the sky is blue, because blue light travels in smaller waves and is thus easier to scatter. Most stars appear redder than their true color, so we have to correct for this reddening in our analysis. To do this, we got a value of 0.3 magnitudes as our reddening value, and we subtracted that from the raw B minus V value to obtain what's called the true color index. Then we also corrected the apparent V magnitudes by subtracting 3.2 times 0.3, and then plotted that using our data. So using Python, we plotted the corrected V values on the y-axis and the true color index on the x-axis. And then we overlaid a Zhang's line, or the zero-age main sequence line, over it. So we kind of created a color magnitude diagram, which is the observational version of the Hertzsprung-Russell diagram, which is pictured here, which shows the different life cycles of stars given their luminosity and surface temperature. So to estimate the age, we found the part of the graph where most stars are turning off relative to the Zhang's line. So for our cluster, the cutoff star was star 141, and we calculated the spectral class of each star, so O, B, A, F, G, K, or M, using the color indexes, and we found that our star 141 was class A, which put NGC 1245 at approximately 1 billion years old. So this is the table we referred to ensure that to get the spectral type of each star. And then we generated this bar graph using Python, which shows the spectral types. And as you can see, the most stars are in class A, which are hot young blue stars, which coincides with what Juan was talking about with the composition of a stellar cluster.
By plotting the corrected V value, representing the magnitude on the y-axis, and the corrected B minus V value, representing the color index on the x-axis, we're able to create a color magnitude diagram. Then, by overlaying a zero-age main sequence line, we are able to determine the turn-off point, or turn-off star, which represents the point at which the cluster, or the stars in the cluster, begin to turn off of the main sequence. Then we can use the turn-off star to determine the age of the cluster.
In order to determine the distance to our star cluster, we have to use the distance modulus equation, which details as 10 to the power of the star's apparent magnitude minus the star's absolute magnitude plus 5 over 5. However, the star's absolute magnitude of any star in NGC 1245 is not known, which is why we have to use a standard star whose absolute magnitude is known, but is similar in spectral class to one of the stars in NGC 1245. For that, we used Eta Cassiopeae, whose color index is around 0.66 and absolute value is 4.59. And we used star 113 from NGC 1245, whose color index was 0.663 and apparent magnitude was 16.352. Both stars were of the G spectral class. In the end, we found that the distance to NGC 1245 was 2,251 parsecs, or 7,338 light years away.
So why do we study open clusters? Open clusters contain many young stars, which provides insight into the star's life cycle and formation. By recording the apparent brightness of stars in open clusters and comparing them to known amounts of light emitted, which is known as the absolute magnitude of other stars, we are able to determine the distance to the cluster. Open clusters also allow us to understand stellar dynamics and populations, and uniformity within clusters and young age of stars aid in exoplanet detection and characterization.
Their strongest points were teamwork and coordination. There was no confusion about tasks, and we all did our parts diligently. In addition, we managed to use Python to automate some of the visuals, which was an impressive task. Our weakest points were the fact that we had to manually perform photometry. This not only left slight inconsistencies and room for error, but also made the project much more arduous and time-consuming. Another difficult element was the time zone difference. As some of us live on the East Coast and others live on the West Coast, it was difficult to find meeting times that worked for all of us. This internship not only allowed me to network and collaborate with my highly motivated peers, but also piqued and cultivated my interest for research in space.
I am very grateful for this internship as it allowed me to do authentic research, which is something that I wouldn't have otherwise experienced. I also gained valuable experience in collaboration as well as collecting and processing data, which will be useful skills to have in my future career.
I'm very grateful for SEAS and this internship as it has given me the opportunity to conduct research and experience teamwork within that research alongside peers who share my interest within the subject. I much better understand the importance of flexibility when conducting research, and I look forward to continuing to do so for many, many years to come.
I'm grateful for SEAS because it exposed me to authentic astronomy research and it gave me the opportunity to network with people who share my same interests.
I truly appreciate the opportunity to be a part of the SEAS internship and the chance to participate in hands-on research in astronomy. This program has solidified my interest in the scientific research in space, and I'm excited to take what I've learned from this program to pursue my interest in astronomy further in the future.
I'm grateful for the SEAS internship as it allowed me to do research with a topic that I've been interested in while working alongside hardworking peers and helping me realize it is something I want to do more of in the future.
We would also like to give a special thanks to Mrs. Kuper for guiding us throughout this internship and Professor Tom Rutherford for providing valuable telescope data. We would also like to thank NASA SEAS as well as all of its partners, including the Center for Space Research and the Texas Space Grant Consortium. And here are our references.